Okay, now a quick overview is we start by understanding the toolkit functions. Which we've graphed in 4x4 rectangles like this or like this, and you should know what I mean by that. Okay, so we can take these graphs where f of x is a toolkit function. Usually in a 4x4 rectangle with a red dot at the origin. Then a f of x minus h times k, and we'll call that maybe g of x. The red dot would move to hk. The rectangle would be 4a times 4. So 4a this way and 4 this way. If you have the origin or the red dot at the bottom of the rectangle and a is negative, you'd flip that rectangle over so the red dot would be at the top. If you have the red dot in the middle of the rectangle, you just have to know that the picture of the graph flips about the x-axis. Okay, that's what negative value of a does. So there's that entire scheme. And then we want to estimate solutions of the equation a f of x minus h plus k equals some number that we'll call c. And or we solve the equation. To estimate a solution, now none of our toolkit functions give us graphs that look like this, but just say we have a function. Okay. If we have a line, let's say y equals c, and this is a graph of some function, g of x. This x value is a solution of g of x equals c. So if we've got an equation, g of x equals c, whatever g of x happens to be, a lot of times in this course, and what we're going to address today, is it's an a f of x minus h plus k function. You can see if you have an accurate graph, a reasonably accurate graph, you can draw the line where y equals c and estimate the value of x. That value is going to be the solution. Now you're going to see that, but we want to kind of put that in perspective. Also, of course, let's say that this is a line x equals a, then if we get this point on the graph, the y value here is just g of a, where we just plug whatever the value of a is into the formula for x and write it out, figure it out, put it into a calculator if it's an ASCII thing, okay? And there's our original picture of the course. Of the toolkit functions, how they can be transformed and so forth. And one thing that I focus on here right early is how do you solve these equations? Because we've done some of that, we haven't looked at it systematically. So now there's much more to the course. Then we have composite functions. We have rate of change, which is related to a fundamental triangle that we want to talk about. We have really important to be able to graphing quadratic functions. And these are things you can expect to see on the final. Okay. And then power functions. Polynomial functions. Rational functions. Exponential logarithmic functions. We also want to mention inverse functions. So some of the things you think about, what words do you think about when you see inverse functions? That means you swap x and y. I'm just going to say it right now, and then we'll work it out. Maybe not today. We've got today and 2 more days to review and pull everything together into a nice package. Okay, so we have inverse functions where you swap x and y. If you got the equation, you swap x and y, and you solve for y, and you get your inverse function. If you got a graph, you swap x and y, which is equivalent to swapping the x and y values in the table. Okay, composite functions, you plug one function into the other. And that's something people still maybe have a little trouble with, especially identifying what the functions are that go together to give you the composite function. Now, rate of change is central idea for the first semester of most calculus courses. That's what the first semester is all about. And you do a lot of algebra with that and so forth. You want to make sure your algebra is up to it. And you use functions, composites, and so forth. There's a whole lot of that in a calculus course. Okay. Then quadratic functions are really important. Linear functions are really important. I didn't mention linear functions because that's pretty obvious. And I'll just go ahead and write it in here. quadratic functions, power functions, and so forth. Okay. And what do you do with the, and then of course you have simultaneous equations and matrices. If the equations are linear, then you have simultaneous linear equations, which can be interpreted in terms of matrices, augmented matrices, and so forth, solved by elimination, and all those things. And then find a function given the type and some graph points. But we did some of that. We did quite a bit of that last week. So you already have that, but I want to still address it in summary so you can see how it fits into the whole picture. So let's take a quick look at what we did in the support course today. And I called it a summative overview of pre-calculus 1, which kind of overlaps the picture I gave you here. Now, I'm not going to go through all the details of this, but it's here. And if you want a fuller explanation, a little slower, you can look at the video from the MDE 61 support course. First of all, we kind of focused mainly on the squaring exponential and reciprocal functions, which have graphs that look like this, this, and this that can be constructed by means that you simply have to know. And everybody here has done really well with constructing those things, at least the first test. And if you haven't got the construction down, you're going to really need it because it will appear on the final. So one of the questions I had at the beginning of the class was, can you tell me what's going to be in the final? Well, yeah, everything. But let's be specific. Okay. So you're going to need to be able to construct these. You're going to need to be able to take an X value and find what the value of f of X is. So you put your X value in a vertical line and your f of X value. Presumably you've got your toolkit function or some transform function already constructed. And given an X, you do the vertical line, see where it hits the graph, and you get a horizontal line, and that's going to be the Y value for the function at that point of X. If you have a Y value, well, you can draw the horizontal line for the Y value, and then a vertical line, and the value of X is your solution of Y equals f of X. Now that should be something that you really understand. People tended to do well throughout the course with making those estimates. Okay, now pulling them together with the formulas gets a little shaky in some cases. In some cases, people know it quite well by now. We have the equations for the exponential functions. I mean, for the toolkit functions, the squaring function is f of X equals X squared, exponential function f of X equals 2 to the X, reciprocal function f of X equals 1 over X. We have domains and ranges. Without a lot of comment, but something you need to be careful of, the domain and range of the toolkit as constructed in the 4x4 rectangles that we're using for these three functions. We would also use the same rectangle to do the reciprocal square function that we use for the squaring function. Cubing function gets a little bit different, and power functions, we need to understand those, but we'll talk about those a little bit later. We've talked about those pretty recently. People are kind of shaky with power functions. Okay, so we do want to emphasize that between now and our last class. But okay, as constructed, the toolkit functions. The scoring function has a domain. Here's your scoring function. Domain is from -2 to 2. And every x value from -2 to 2, if you draw the vertical line for that x value, it's going to hit the graph. So every one of those x values is in the domain. And I wrote -2, -2 there. That was zoom in. The domain is from -2 to 2. The range, well, if you draw a horizontal line for any number for any y value, it's going to hit the graph, usually in 2 points. It's going to hit the graph. All it has to do is hit the graph, then it's automatically in the range. And all these numbers are in the range. So the range is from 0 to 4. If you look at the exponential function, again, every vertical line within this rectangle is going to hit a point of the graph, but not every horizontal line will. So every vertical line hits the graph. That means that every one of your x values from -2 to 2 is in the domain. Not every horizontal line hits the graph. Now, it does if you draw the graph wrong, as many people have been in the habit of doing, although I don't think too many people mess that up on the exam, okay? People want to put the first point at the lower left-hand corner of this graph, and that's not right. It's on the construction line directly above the lower left-hand corner on the line y equals 1/4. So that the range, if you try to hit the graph in this rectangle with a horizontal line lower than the y equals 1/4 line, you ain't going to hit it. Now, if you extend the graph on to -infinity this way and +infinity that way, yeah, you will hit it with any x value above the lower left edge, or any y value above the lower left edge here, any positive y value. You'll never hit it with a negative y value. Okay, well, graphing within this rectangle, the domain is -2 to 2. The range is 1/4 to 4. Because again, when x is between -2 and 2, you don't have any y values less than 1/4. But you do have them all the way up to 4. And then the reciprocal function within the constructed graph, it looks like this. I didn't do a real good job of getting these lines in the right place, but they're approximately good. We sketch this part of the curve and this part of the curve. We don't cross the y-axis, the line where x equals 0, because the pattern is every time we go twice as close to that center line, and let's kind of emphasize that center line for a minute. Right there's our center line. That's the x equals 0 line, which is also the y-axis. Every time we go twice as close to the middle, we go twice as far from the horizontal center line, the line where y equals 0, or the x-axis for our basic toolkit function. So we go twice as close to the center, we go twice as far, twice as close to the vertical center, we go twice as far from the horizontal center. And we keep doing that. There's no limit to how many times we can go twice as close to the vertical center. So there's no limit to how many times we go twice as far as we just were from the horizontal center, which means if we go twice as close here, we go to the vertical line about here, we have to go twice that far down, which is off the board. If we do that 100 times, well, we passed through the center of the earth a long time ago. We're out past the orbit of the moon, most likely, okay? You double 100 times. If you start with 1 and double 100 times, you have a number that's bigger than the number of atoms in the earth. Okay. And you can imagine how far that graph would have to go. It'd have to go out to the end of the universe. Okay. End of the known universe. Which you get to if you travel at the speed of light for about 15 billion years. Okay. So these numbers get really big, meaning you have a vertical asymptote here. That's what we're really talking about. And you have a vertical asymptote over here because the same thing happens on this side. You also approach the x-axis because here you're doubling your x value from here. You go to here, then you double it, then you double it. And each time you go twice as close to the x-axis. Every time then you double your x value, your y gets twice as close to the x-axis, but it never reaches it. And you have a horizontal asymptote. Okay, important to understand those things. We've talked about it, but you know, it's not a process that we've really emphasized, but you could have questions related to that process. You want to be aware of it. Okay. To sketch the transform graph. Okay. Okay. Where you're stretching and shifting transformations, there's also a horizontal compression that is relevant to your exponential functions, and you've seen that in the assignments. But right now I'm going to just stick to the first three because they really don't start applying until you get to the exponential function. And then if you take second semester, you have your trigonometric functions, and they need to be compressed and stretched in both horizontal and vertical directions so that you can really begin to model the universe. Okay? So hopefully by the end of the year, you'll be able, or the end of the academic year, you'll have a good model of the universe in your head. Well, that's probably a stretch because nobody really has one. Okay, well, end of digression. Stretching and shifting transformations. Y equals f of x minus h shifts your f of x function, whatever it is, plus h units in the horizontal direction. Y of f of x plus k shifts plus k units in the vertical direction. And a f of x stretches in your vertical direction by factor a. Also, it reflects through the x-axis if a is less than 0. And also, if you wish, if a happens to be, I wrote it down wrong, if absolute value of a happens to be less than 1, it compresses. Okay. Then in general, if you do all three of these things, you get the function y equals a f of x minus h plus k. Now, what does that do? That takes your 4x4 rectangle with the red dot where it goes for the given function at the origin and moves that red dot to the point hk. Now, actually, we don't want that. Let's see if we can find what we want. Yeah, here it is. Okay. So f of x equals a f of x minus h plus k can be constructed in a rectangle where hk here or here is the coordinate of your red dot. So you simply draw a rectangle, say that put the red dot where it goes for the given function. And that's your point hk. The dimensions of the rectangle are not 4x4 anymore, but if your width is 4, as it is in both of these pictures, then the height of the rectangle will be 4 times A, not 4, but 4 times A. Why? Because A is your vertical stretch factor, and your Y values will have to range over 4 times the original 4 units, or A times the 4 units. So graph will be 4A by 4. Either way, either type of function. And the red dot might be at the top. If A is negative, that's going to flip the graph around the x-axis. And the red dot will have to be at the top. And if you got like a squaring function, it's going to open upside down. If it's an exponential function, it's going to be a decreasing exponential. If it's a reciprocal function, then instead of having a curve here, you're going to have one up here. And instead of having the curve up here, you're going to have one down here. I'm not going to draw that. But you should understand that. And if you want me to draw those, let me know and I'll draw them in a different place. Actually, I actually go ahead and draw them. If A is greater than 0, then, for example, this curve will look like this. It's not very well drawn. If A is less than 0, then you still have the same dimensions. If you have the reciprocal function with your red dot in the middle, you flipped it across the x-axis, and that's going to put this side up here and this side down here. And of course, that's the same thing you'd get if you flipped it around the y-axis. There's a symmetry involved, but I'm not going to talk about that right now. If you have a function where the red dot is at the center of the lower edge, then if A is less than 0, it's going to go at the upper edge and your graph's going to be upside down. Okay? So it's still 4 by 4. That's not 4 by 4A. The red dot is still at HK. Here or here. But the graph, like your squaring function, will have a graph that kind of looks like that. Your exponential function will have a graph that kind of does this. Okay? You should recognize those as upside down squaring function and an upside down exponential function. And there are other details, but there's a general picture. Okay. So we basically know how to construct these graphs, at least for those 3 functions and some of the others. Okay. Now, what's the equation? Well, first of all, what is the form of f of x minus h, af of x minus h plus k? Well, it's fairly straightforward. If f of x equals x squared, then f of x minus h will be f of x minus h equals x minus h squared. You replace x here with x minus h, and you get this. That's it. So that a f of x minus h plus k is just a times your x minus h squared. That's what your f of x minus h is, plus k. Similarly, if you replace the x's in f of x equals 2 to the x by x minus h, which is just what this always does, then you're going to get f of x minus h. F of x becomes f of x minus h, and 2 to the x becomes 2 to the x minus h. So that you're a f of x minus h plus k. Well, once you've got f of x minus h, it's easy. Just put an a in front of whatever it is and add k in every case. Okay. If f of x is 1 over x, then you replace both x's by x minus h, and it becomes f of x minus h equals 1 over x minus h. Then you put an a in front of that and add k, and you have your transform function. If it's 1 over x squared, well, you do the same thing. It's getting old. You replace x by x minus h, and you get this. And then you put an a in front of it and add k, and there's your function. If it's x cubed, well, you do the same thing. Okay. And then if you know how to construct the graph, I mean, the first part is really easy. You know where the red dot's going to go. It's at hk. And you know what the dimensions of this rectangle would be. So you can sketch the graph of a f of x minus h plus k, at least in a rectangle that's 4 units wide, knowing where the red dot is, and knowing that the height of that rectangle is 4 times whatever a is, because a is your vertical stretch factor. We stretch it from a height of 4 on the toolkit graph to a height of 4 times a. It gets a times as big. Or if a is less than 1, it gets squashed down. All right. So those are the equations. Okay, well, what is your equation then? Okay, because what we're wanting to do is like solve the equation. So here we got, let's say this is a value of c. And whichever graph it is, I'll just draw it in this one. Then if we're doing the squaring function, we'd want to find the vertical lines through the points where the y equals c line intersects the curve. Or if it's an exponential function, we want to find the x value for the one point where the y equals c value intersects the curve. And we'll illustrate that shortly. What are the equations? Well, the equation a f of x minus h plus k equals c has an approximate solution that you get just by sketching the graph and doing what you learned to do in the first day, or at least in the first week. But if we want to actually solve these equations, what do we do? Well, again, for the squaring function, this equation would be, well, here's the form of your AF of x minus h plus k, a x minus h squared plus k equals c, corresponding for the exponential function, or the reciprocal function, for the reciprocal square function, and for the cubing function. Those are our equations. How do we solve them? Well, if you have a transformed squaring function, which is a quadratic function, then your AF of x minus h plus k equals c equation is this, same as what I wrote on the previous board. How do you solve that? You're trying to get x. You got a plus k on the same side as your x stuff, so you're going to subtract k from both sides, right? Then you got an a times an x minus h squared. Some people want to add an h, but you can't do that because the x minus h is squared. It's not just an x minus h. You divide by a. And then you have something squared equals something else, where the x is inside the square. You take plus or minus the square root of both sides, and you get x minus h is plus or minus the square root of this. And then add h to both sides. You get x equals h plus or minus square root of this. Now, you should be able to do that. If I write out this form, you should be able to do those steps. But with numbers, it looks like this. If your vertical stretch factor is 2, your horizontal shift is -3, and your vertical shift is 5, then number 1, you can construct this in your standard rectangle, going in a rectangle with a red dot at HK. Okay, lower middle of the lower edge of the graph, and I'll just kind of sketch that. If I can find the red. Okay, so we've got this graph. And we've got y equals c. We have a vertical line here and a vertical line here, and these are two solutions. This point is hk. H is -3. K is 5. So there's a picture. We could estimate our solutions and compare them with the solutions we get if we do the straightforward algebra. Now we have to be able to do the algebra, so you have to understand the algebra. Well, clearly you got a +5 here. You can subtract that from both sides, and you get 2 on this side. And then the x minus -3 becomes an x plus 3. It's squared, so we can't really do anything inside of that parentheses, that set of parentheses. So we divide this 2 on both sides, which leaves us just x plus 3 squared equals 1. And then we do plus or minus the square root of this. That corresponds to plus or minus the square root of c minus k over a. That's what we've actually done. And we get x plus 3 equals plus or minus 1. And then x equals -3 plus or minus 1. So x equals -4 or -2. And then we put those numbers back in here and they check out. They also check out with this picture if you draw it accurately. And I have that. Matter of fact, I have it right here. So let's just see what it looks like in this case. I haven't done that for every one of these functions, but. Okay. Again, here's a times quad ax minus h squared plus k equals c for the same values of a, h, and k. The rectangle is 4 units in this direction and 4a units in this direction. A is 2, so it's 8 units in this direction. The red dot is at hk, which is -3, 5. From that, you can see, well, this thing's 4 units wide. This is right in the middle, so you got 2 units here and 2 units here. If x is -3 in the middle, you go 2 units to the right, you get x equals -1. You go 2 units to the left, you get x equals -5. So you can sketch this thing. You can sketch a nice accurate graph. This has actually turned out fairly accurate, despite the fact that I drew it freehand. Okay? Doesn't always work that well. And c is 7, so we're setting this thing equal to 7. Well, y is 7. We draw the y equals 7 line, and there are 2 points where we intersect the graph, and we draw the 2 vertical lines and estimate the x values. When I estimated the x values here, it turned out that I was right on a construction line here, so x is -4. I was a little to the right of this construction line here, which gave me x equals -1.8. Now, we compare the estimated solution set, which is -4, -1.8, with the solution set that we got when we solved the equation, which was -4, -2. Okay, so you probably pull this over where you can see most of it. Let's see if I can make it all visible. Yeah, we got it. Okay, so here's the equation with the same values of a that I used to construct this graph. My solution set here was -4, -2. My estimated solution was -4, -1.8. Of course, I could check by plugging -4 and -2 back into the original equation, but it helps to also be able to see it graphically. Because a lot of times, what you end up doing is using a graphing calculator or a Desmos or something on a computer or some online resource, okay? And you're gonna have a picture. If you want to do a picture of this function, you want to know what window to put it in. Now, maybe you do a big picture and you keep zooming in, but it's nice to know before you start what you want to look at. You want to look at the vicinity of -3, 5. So you know that -3, 5 has to be in your window. So you build a window around -3, 5 to find what you need to find. Now, we're not doing the graphing calculator. I'm just saying the reason we're talking about these windows is that when you get your hands on a graphing calculator in another course or some other point in your life, you'll understand that there's a way to figure out what your window looks like and what your function should look like so you can find what you want to find. So you want a window where you could, that y = 7 line is easy to find. You can draw that graph. You can tell the graphing calculator, show me the line y = 7. And then you can zoom in on these points and estimate your x's and y's. Okay. And you have to do that for some complicated functions. These functions, you're better off doing it algebraically so you understand what's going on better. Okay. Now, we also solve the same equation for the exponential function. So you end up with same values of h and k. You end up with 2 times 2 to the x minus h, which is x minus -3, plus k, which is 5, equals 7. Same numbers. Then we simplify. Simply, the only thing we've done here is replace the -3 by +3, because you really do have to be careful about negative signs. You've seen me make mistakes about negative signs. You've made mistakes with negative signs. Everybody makes mistakes with negative signs. That's why you check things. Okay. So now the solution's pretty simple. You follow almost the same steps you did before. You subtract the 5 from both sides. You get a 2 over here, and the 5 disappears on this side. And you have 2 multiplied by 2 to the x plus 1 equals 2. There are various ways to solve this. Turns out that 2 times 2 to the x plus 1 is just 2 to the x plus 2. But we're not going to bother with that. We're just going to divide both sides by this 2. You get 2 to the x plus 1 equals 1. Okay? Now you could solve the equation at this point, because you know that the only power of 2 that equals 1 is the 0 power. 2 to the 0 equals 1, so x plus 1 had better equal 0. But we get that by following the procedure we would need if x was, like, instead of 7, it was 8. Say 10, okay? If this side was 10, then we'd be getting subtracting 5, we'd be getting a 5 here, and we'd have 2 to the x plus 1 equals 5. You can't tell me what power of 2 equals 5. You can say it's probably between 4 and 3, between 2 and 4, because 2 squared is 4. I'll get it right yet. Between 2 and 3. Okay, 2 squared is 4, 3 squared is 9, and 5 is between 2 and 9, right? So you know the solution of 2 to the x plus 1 equals 9. Well, most of what I said in the last couple of sentences is garbage, so ignore it. Okay. My point is, you want a general form. If this is a 5, you would know then that the power of 2 has to be between 2 and 3, because 2 squared is 4, 2 cubed is 8, and 5 is between 4 and 8. If this is 5, you'd know that x plus 1 would equal something between 4 and 8. Well, it's handy to know in a lot of cases. You don't need to know that. This is an exponential equation. Your variable's in the exponent, so you switch this to logarithmic form. Now, if you don't remember how to do that, review it. Okay. I'll just make a quick note that B to the A equals C is equivalent to A equals log base C of B. Now, that's something that you should know well enough that it interferes with your sleep at night. Okay? You have to know that. But once you know that, it's real easy to solve exponential equations. So, that's just the inverse function property. We've talked about that. It's to some extent, and I'll probably talk about it a little more when we get into a little more detail. But using the inverse function property, the fact that the log is the inverse to the exponential function, you can change this equation to this form. And then log base 2 of 1 is something you can simply calculate. It's log of 1 over log of 2. And you can evaluate it on your calculator if you need to. Now, if you already know that log of 1 is always 0, and that's because any number to the 0 power is 1, something you should know, but don't necessarily have to. In any case, this simplifies to x plus 1 equals 0, and you solve that and you get x equals -1. Then you plug that back into the equation and see that 2 times 2 to the -1 plus 3, which would be 2 times 2 squared, doesn't equal 7. What's wrong here? The problem is that it wasn't 2 to the x plus 1, it's 2 to the x plus 3. When I did this in the support class, I didn't check. So here I am with a bonehead error for everybody to see. But that's not unusual. So let's just make that a little prettier. It's 2 to the x plus 3. I was thinking ahead to the 1. No excuse. But now my equation becomes x plus 3 is log base 2 of 1. Same idea. So x plus 3 is 0 and x is -3, and that works. Because if x is -3, then 2 to the x plus 3 is 2 to the -3 plus 3, which is 2 to the 0, which is 1. 2 times 1 is 2. Add that 5, you get 7. Be careful. Like sometimes I guess I'm not. Okay. All right. So that's how you solve the exponential equation. And you're going to need to be able to do that. And we see how you go. Okay, reciprocal function, the same values a, h, and k. You're going to have 1 over x minus h is 1 over x minus -3. So you got 2 times 1 over x minus -3. Well, x minus -3 is x plus 3. 2 times that is 2 over x plus 3. Plus 5 equals 7. So now that we've rearranged and simplified, we have this equation, and we subtract 5 from both sides, getting this equals 2. Same as we've seen in every previous equation. We're always going to subtract this from this at some point. Then we have this, so what do? We multiply through by the common denominator. You've got a denominator here. But you get in the habit of, after you get things simplified, you multiply through by the common denominator. So we multiply this side by x plus 3. We multiply this side by x plus 3. Okay? Now, when we multiply 2 over x plus 3 by x plus 3, it helps to write this as x plus 3 over 1 if you're not really secure with rules for fractions. Then you can see that when we multiply numerators, we get 2 times x plus 3. When we multiply denominators, we just get x plus 3. On this side, multiply x plus 3 quantity by 2, we get 2x plus 6. And I wrote this down carelessly. See how my 6 is kind of smudged out? That's because I had a 3 here instead of 6. I didn't multiply my 2 by 3. I got something down here that didn't check. Okay, I got something on this one that didn't check, but I didn't check to see. Here I checked and I found that I had an error, just a very common, simple error that I shouldn't be making. Now, 2 times the quantity x plus 3 over x plus 3. X plus 3 is a factor of the denominator, and it's a factor of the numerator. So we can divide this x plus 3 by this x plus 3. Gives us 1, so this just simplifies to 2. And you can say those things cancel. I don't like it because people do it wrong. You have to understand it's a factor of the denominator and a factor of the numerator. Okay? But some people know that. Some people are still shaky with it. So I don't like to start crossing things out. Anyhow, got 2 equals 2x plus 6. And we solve that, we get x equals negative 2. Plug it in up here and it checks. Okay? So that's examples of how we solve some of these equations. Okay? And I think that's pretty much what I already have. So let's get to some of the specifics, some of the specific functions. Okay. The nicest form is this because you can easily graph it. The vertex you can identify your vertex in the vertical stretch A. Now, actually, I want to use the lowercase a for the quadratic function, because now when you expand this, you might do the x minus h squared plus k. You get x minus h quantity squared is x squared minus 2hx plus h squared. And then you simplify that and you get ax squared plus bx plus c. B is just going to be a times your negative 2h. And c is going to be a times h squared plus k, but you don't need to necessarily know that. If you were to multiply this out for actual numbers like we used before, you would naturally put it into this form. Okay? G of x equals 2 times the quantity x plus 3 squared plus 5. Is 2 times the quantity x squared plus 6x plus 9 plus 5. And I assume you can use the distributive law to square x plus 3. If you can't, email me. Okay. But I'm not going to take time in this overall review because we've stressed the distributive law a number of times. If I've done my arithmetic right, this is 2x squared plus 12x plus 23. Okay. Now, it's easier to graph in this form. We just saw that. But if you have this form, you have a couple of options. One is you can complete the square to get this form. Now, I make a controversial choice in this class. 95% of the class is not equipped to understand completing the square. Most of the people here today are, but I'm not going to do that. Just don't do it in this class. If you see it in a later class, if you understand everything we've done in this class, you're not going to have any trouble understanding it. Okay? Yeah, you might have a little trouble, but it's really not difficult if your algebra is up to it. And I would love to teach this class in such a way that everybody's algebra comes up to it. But people are starting this class, not necessarily present company, but too many people are starting at way too low of an algebra background to be able to do everything we should be doing in this class. It's because anybody can put themselves into this course. People have been getting good grades in their math courses, and they think they're no algebra, but you know, it's too bad. And you can't convince them to take a support course or an intermediate algebra course first. Okay, that's my excuse for not completing the square. And if you find that you've been unnecessarily deprived, I apologize. But I don't think you'll have any trouble with it if you need it. Okay, so what do we do here? Well, we use the fact that the equation ax squared plus bx plus c equals 0 has solutions x equals negative b plus or minus, etc. Okay? The familiar quadratic equation, which I keep trying to convince people tells you exactly where the vertex is. So here's a quadratic formula. First thing it tells you vertex is on the axis of symmetry. X equals negative b over 2a, which is negative 12 over 2 times 2, which is negative 3. Well, just back to wherever I put it, the graph of our function. Let's just review the fact that, what did we find? We found that this function that we've been talking about has an axis of symmetry at x equals -3. We'll look at it. Right there it is. Okay. This should convince you that you can find the axis of symmetry if you just write out what the quadratic formula tells you. Okay. Now, another thing about that graph is that vertex was at -3, 5. So the y-quarter of the vertex is remember, our function is g of x. It's a g of -3, and we'll use this form instead of this form to see what the vertex would be. Okay, we get 2 times -3 quantity squared plus 12 times -3 plus 23, which equals 2 times 9 minus 36 plus 23, which equals 5. Again, just to check our consistency, -3, 5. That's where our vertex is. If we drew it from the vertex form, we would get that vertex very quickly. Because of course our vertex is hk, and h for this function is -3 and k is 5, right? If we don't have the vertex form, we either put this in vertex form or we use this. Since I haven't shown you how to put this in vertex form, and if you want, you can look up completing the square. Okay. If you happen to use completing the square on the exam, probably give you a couple extra points. It's worth knowing, but first, make sure you understand everything else. Okay. Okay. Now, 4 times 2 times 23 is 160 plus 184. So I think a little bit of a question mark on that -40 because I did that very quickly in my head. You get x equals -12 plus or minus the square root of -40, I think, over 4. The one thing I know is that 4 times 2 times 23 is bigger than 12 squared, which is 144. 4 times 2 times 20 is 160. Subtract 160 from 144, you get a negative number. It's got to be 24 more than that, and I just confirmed the -40 for myself. But, you know, if you do the arithmetic, I think that's what you're going to get. One way or another, you are going to get a negative. It's not a real number. You have no zeros. Well, that means that the graph doesn't intersect the x-axis, right? Well, here's the graph. Is this graph going to intersect the x-axis? Well, where's the x-axis? It's at y equals 0, which is something you got to always remember, right? So y equals 0 is going to be down here. This thing's opening upward from a point above the x-axis, so it ain't going to hit the x-axis. Now, you also have the y-intercept. I didn't leave myself room to write down. I just kind of open myself a little box here. Y-intercept is that y equals g of 0. If x is 0, you're going to get 23, which is a lot easier from this form, in this form than it is in this form. So y equals 23, right? If we put that onto the graph, and left myself plenty of room over here. If I'm going to draw a graph of this thing and don't want to use this window, I can say, okay, well, my axis of symmetry is that x equals -3. My vertex is that on the axis of symmetry. And it's at y equals 5. So here is our red dot. Okay. And up here is y equals 23. It would actually be a little higher than that. But so we got to have a parabola that goes through this point and this point. Goes through this point with this point being the vertex. So we could sketch that. Okay. Fairly easy to sketch. Yeah. Chalk's getting away from me. Okay, it's not a great sketch. If I wanted to make a better sketch, I'll just do it real quickly, so you don't need to know this. But it's kind of handy. I can just draw a box, a rectangle with this thing at the midpoint of the lower edge, and I can divide it up. And I can see that my points go right where they ought to go. Actually, those aren't right. Should be here. So, yeah, a little lower and a little higher. Semi-graph would look more like this. Now, you know what I did with that rectangle. I hope you do, because you got to be able to do that. So you can always do that if you know the vertex and a point on the graph. You can always draw the rectangle and draw a nice graph. Okay. Just make sure the rectangle, make sure the red dots at the vertex, at the midpoint of your lower edge, and then your upper edge could be the other point. It's a little enhancement. You don't have to know that. I'm not going to test you on that, but if you do that, it's a nice way to get a good graph. Okay, so now where are we? I started out by okay, give me a minute. Here we go. I'm knocking everything off my stand. Okay. No, that isn't it. What's the other side? Okay. Now we didn't get into polynomials and exponential functions and so forth, but we did get into solving a lot of these equations. Polynomial equations, as we'll talk about next time, you just factor them and set each factor equal to 0. I mean, make sure that you have the polynomial equal to 0, then you just make sure everything's factored. In a lot of cases, I'll give you the polynomial in factored form. And you can find the zeros easily and then graph it. And so forth. Well, we'll review that next time. So we've really talked about this. We haven't talked much about linear functions. When we're going to relate these to the fundamental triangle, we're not going to spend a lot of time on it because they're pretty simple. The idea of rate of change is something you should be familiar with if you're constructing fundamental triangles, finding rates of change. We'll enhance that a little bit. I'll talk little bit more about composite functions. How do you recognize the inner function and the outer function? And power functions, which are really pretty simple if you understand the scheme. But I don't think everybody is quite up to speed on that scheme, so we want to make sure we get that. And then polynomial functions that we just talked about, you just figure out where the zeros and the y-intercept are in the long run behavior. Rational functions, then you got to also worry about vertical asymptotes. Exponential logarithmic functions aren't all that bad if you know how to convert from exponential to logarithmic form and back, okay? Then simultaneous equations and matrices, which we've just finished up with. And don't know if you looked at the thing I gave you for last Thursday, not Tuesday. I think, well, not that many people made it on Thursday, but make sure you look at the thing that was posted for last Tuesday, because I think it's pretty well done. I think it's pretty clear. If you have any problem at all with the simultaneous equations and the matrices, and the reduction of the augmented matrix, a lot of people have that down pretty well. If you don't, use that video or use one of the other videos. One last thing, is anybody having trouble viewing the videos? I got from one member of the class who was clicking on the videos and they were just taking him back to the page he was on. Okay. And I investigated it and found out, yeah, that happens on my computer too. It doesn't happen when I access the assignments in the way I usually do, just by clicking on them in the gradebook. Okay. But if you do it from the web page as you see it, you can't do that. So I was not aware that that was a problem, but it has to do with cookies and a lot of other stuff. Okay. You probably want to maybe switch your browser or something. But if you're having trouble with that, anybody in the course, anybody who's not here, please let me know, because I can go through these assignments and pull out the correct video links and list them for the help functions. Okay. So that's apparently been going on with somebody who's not been able to make it to class. He has valid excuses, reasons he can't make it to class. He's keeping up with the homework. And who's doing quite well. He's been suffering with that through the whole course. Still doing a good job, so more power to him, but he finally told me about it and we resolved that. So if you're having any trouble accessing the videos, the help videos in the homework, please let me know. I don't think there's a problem with the links to the videos on the assignments page, but sometimes you want one that focuses on the problem you're looking at. So use whatever's going to work for you. Okay, that's it. Have a great Thanksgiving, and I'll see you in a week. Email me if you have problems. I'm glad to answer questions. If you're behind on the homework, get into the half credit page and get it done. Some people have been a little sporadic with homework, both, people have been making it class and people that haven't. So it's a way to prepare.